So Javier got his PhD in 2013. He studied with Diego Cordoba. He then moved to Princeton, where he was an instructor from 2013 to 2016, and then an assistant professor until recently. In 2019, he won the ERC starting grant, and starting this fall, he'll be splitting his time between Brown and University of Barcelona. So Javier is expert in computer-assisted proofs for PDEs. If you're interested, there's a recent review article of Javier's on our resources part of the webpage. But this morning, we're delighted to hear about uniqueness of Whitham's highest cusp wave. So Javier, it's all yours.
Thank you. Yeah, thanks a lot for the nice introduction, and thanks a lot for the invitation. First of all, can everybody hear me well? Is it okay? Okay, perfect.
Good.
Yeah, so today I'm going to talk, so my title, say my serious title is Uniqueness of Whitham's highest cusp wave. And not so serious, but probably more truthful, is how I stop worrying and learn to love special functions. So there are a lot of special functions in this talk. And at first, we thought those were the enemy, and we were not so happy about them. But it turns out that they saved the day for us. So I will explain how special functions are going to play a role, and how they are going to be helpful for our purposes. So this is joint work with Alberto Enciso, who is at ICEMAT, and Bruno Vergara, who is at University of Zurich, but he's going to move to University of Barcelona starting next fall. Okay, so yeah, there is also a small disclaimer. I'm new to this like iPad business and giving talks with iPad, so I apologize in advance for like any technical problems. Okay, so let me summarize the talk. So this talk is going to have two parts, and the main takeaway message is that this is not just restricted to one equation, but this is a new strategy to construct and to find singular solutions to PDE in a very broad sense that arise at endpoints of bifurcation branches, and I will explain more what this means, that are non-smooth. Okay, typically the problem with those solutions are that they are non-smooth, and if they can be found, usually it's in a non-constructive way. Okay, so we learn a lot about those solutions, and moreover, this is also sort of a technique to show uniqueness of operators that don't have nice properties, like for example maximum principles and so on. Okay, so the ideas here are going to be pretty simple. It's not like a very deep thought. There is some work, but the main ideas are simple, and I hope to convey the ideas easily. And as I said, we obtain also qualitative information of the solution. Parts of the proof are going to be computer assisted as expected. This doesn't really depend so much on the PDE. So the PDE itself is not very important, and one can find solutions in like bad situations whenever one has like ill-posedness, or whenever one is trying to find like low regularity solutions. So the PDE is not very important. I mean, it is important to a certain extent, but not a lot. And the main message is also that the special functions are your friend and not the enemy. Okay, so let me start with the motivation and talk a little about the Whitham equation. So the main problem, the main physical problem that I want to model is that we have a fluid, like a wave, and there is some bottom, and I want to study the behavior of this interface that separates the water and the air. Okay, so a very famous model, a very well-known model is the Kav equation. Okay, so I want to understand the behavior of this interface as time evolves, and but there are certain issues with using the KdV for modeling in certain regimes. That are, for example, the first one is that the KdV is a local equation. So if you look at the Euler equations, for example, those end up being non-local equations. So this is probably not a good idea in some regimes, and it doesn't really capture some phenomena that we see in real life. So for example, wave breaking, or the formation of crests, or in general non-smooth solutions, and so on. So probably the KDB is not a great model. So let's try to correct the model. Because the purpose of this talk is to find, or I'm interested in finding solutions of greatest height. That means the difference between the crest and the trough of the wave. And those solutions may be bad in the sense that they may develop corners or cusps or some kind of non-smooth behavior. Okay, so KDB, one way to look at it is coming from Euler. So the dispersion relation for Euler is coming from this symbol, hyperbolic tangent of xi over xi to the 1/2. And then if one does a Taylor approximation at xi is equal to 0 to second order, then one finds this and this. And this is precisely, if you substitute into the equation, what gives them the KDB equation. Okay, so sort of a reasonable proposal is to say, well, don't use this approximation at 0, but instead use the full symbol, use the full dispersion relation. Okay, and this is what Whitham did. So the Whitham equation is the following: we have Vergara's term, and then there is some dispersion with the symbol coming from the Euler equation, which is added to this Vergara's type equation. Okay, so yeah, so for small frequencies, then this is essentially like KDB, and the solutions behave in the same way, meaning that for small time and for small frequency, those solutions are going to behave similarly, whereas for large frequency, then this is where really the difference is starting to pop up, because now this tangent is like 1 at infinity, whereas before we were sort of assuming that this was like C. Okay, so the main difference between KDB and Whitham is going to come at large frequencies. So for large frequencies, essentially this goes away, and now the dispersion relation is like 1 over square root of C. Okay, so this is the main difference, and this is like a very weak dispersion relation. Okay, so now this new equation, the Whitham equation, is non-local, so this is good. It's fractional and it's inhomogeneous due to this hyperbolic tangent. So the scaling, there is no like reasonable scaling here that is going to work. Okay, so what do we know about Whitham? Local well-posedness is standard. Global well-posedness is still open. There are traveling waves constructed using local bifurcation by Enstrom and Kalish in 2009. There are also solitary waves by a paper by Enstrom, Groves, and Valen. Klein and So did numerics, and they showed, or they saw that that there was finite time blow up in the form of wave breaking, and also in other forms, and they constructed asymptotics close to the blow up. And Berancourt proved wave breaking. Wave breaking essentially means that your wave, sort of the derivative, blows up, whereas the L infinity known stays bounded. So there is a shock forming. Okay, so this is known for the Whitham equation. So Whitham himself conjectured the following. Whitham in 1967 said, well, if you follow the branch of traveling waves, there is one, which is the highest one, meaning that the highest distance from crest to trough, that moreover has C1/2 regularity. And he did that sort of in a formal way, counting powers and looking at the operators, but this is sort of his conjecture about 50 years ago. So Enstrom and Valen proved prove his conjecture, and and they showed that there is a limiting traveling wave of exactly this regularity. And to do so, they use a global bifurcation argument. So the proof is technically difficult and it's ingenious. But the drawback is that the proof is non-constructive. So they can show that there exists one solution, but they cannot say anything about the solution. For instance, they cannot say whether there is more than one solution. Okay, so in the paper, they also make some additional conjectures, which are the following. So they say that that the wave, the highest wave, is convex, and it has the following asymptotics close to the crest. So this is in the moving frame. There is a term of size 1/2, and the next order is of size less than 1 or more than 1. And mu here is the speed of the wave, and this is part of the problem, and it has to be found. Okay, so this is the conjecture raised by Enstrom and Valén in the paper, and that's so up to here. This is what Whitham conjecture, and they also sort of say something about the next order there. Okay, so just to compare Euler, so this should be like to the Euler. I mean, I wrote it as water waves, but this should be when the motion of the fluid is governed by the Euler equation. So for water waves, some more is known because there is more structure, and one can use like complex analysis tricks to prove certain things. So the existence of of this limiting, which is known as the Stokes wave in the water waves community, was proved by Amick, Frenkel, and Tolan, and Plotnikov and Tolan in the 80s. But then from the existence to the convexity, this happened to be 25 years later. Okay, so we had to wait for 25 years to go from the proof of existence to the proof of convexity, and then from the convexity to the uniqueness, it's about 6 years. Okay, so when we started working on this problem, Bruno was visiting me at Princeton in 2017, and we thought, well, this is a nice problem. Let's see if we can do something. Okay, so about 2017 is when we started working, and in 2018 we released a paper proving the conjecture of the convexity of these traveling waves, and also the proving the conjecture of Enstrom and Valén regarding the asymptotics of the profile. And very lately, we have managed to prove the uniqueness. So uniqueness implies local uniqueness. By local uniqueness, I mean that you have uniqueness in some ball, but what we can prove is full uniqueness under very mild assumptions. So this implies this, but we can prove the whole thing. Okay, so this will be released in a few weeks. We are sort of checking that, doing the final checking of everything, but we are very confident that this works. Okay, so today I'm going to talk about this and about this. Okay, so the first theorem is the one that I mentioned before concerning the existence. So there exists a 2π periodic highest traveling wave, which is cusp, and it is convex, C1/2, and it has the right asymptotic, the asymptotics that were conjectured by Enstrom and Valén for some very, very tiny value of theta, which we don't care, and we didn't even try to compute. Okay, so this is a cartoon of how the branch looks like. So we start with a flat wave, and then we perturb in some suitable direction, and sort of as we travel along the branch, then we go from the black to the red into the blue, which is meant to be sort of something that is very close to the end of the branch. Okay, so this would be sort of this should be close to the limiting limit. Close. Okay, I'm not claiming it's the limiting wave, but it's sort of close. And these are all numerics. I claim no proof concerning these pictures. Okay, so let me explain how the proof works in the case of the existence. So we first put everything into the moving frame, and we don't have to worry about time derivatives anymore. And then this is what the Whitham equation becomes. So we have some nasty linear operator, and then a quadratic part, and okay, some linear part. And then Whitham, in his book, made some heuristic arguments counting powers and claiming that the right asymptotics should be of this type. And one can also see that this is like gaining half of a derivative. So this should be close to 0. This should be like multiplying by x to the 1/2, and it has to be compensated by this term. So phi should be roughly by x, like x to the 1/2. Okay, and this is also like very hand wavy, but just to give an idea that 1/2 is the right power. Okay, so now let me get rid of the linear term, in phi. Okay, and this is easy because I can just consider u, which is mu over 2 minus phi, and therefore when I set it into the square, then it cancels out with the other phi. So now the u should look like something like this. This should be like, let me try to put it like this. This should be like u. Okay, and now our equation becomes even simpler. U squared is equal to LU, and L is this funny integral operator that depends on the dispersive multiplier via the kernel K. So this is a singular kernel and unpleasant. Let me just put it like this, because it's defined via some Fourier series. I mean, that's one way, or if not, then through another integral. Okay, so the first thing is that if we know u, then we know mu. So we don't need to worry about finding back mu, because once we know u, then we can recover mu. Okay, so we have essentially gotten rid of mu, and now our only worry is to solve this equation for u. Okay, so here's how we are going to do it. We're going to yes.
Just a question. So how regular is K? How you said that it's defined in terms of Fourier series. How much decay does it have?
Not a lot. K of x is like 1 over square root of x.
Okay.
So you can sort of define, the symbol is the hyperbolic tangent of xi over xi, everything to the power 1/2. So neglect the hyperbolic tangent, because what you're really worried here are the high frequencies and the tails of everything. So essentially your multiplier is like 1 over square root of xi, which is, if you move to the space domain, then you get like decay in the kernel as 1 over square root of x. Okay, so it's either 1 over square root of x or 1 over square root of xi, either way.
Okay, thank you.
Okay, so we're going to try to construct by hand some approximation u0, and then we're going to try to find a solution close to the u0. And of course, we will succeed or not depending on whether we can construct a sufficiently good u0. Okay, so if I now write my solution as u0 plus u bar, where u bar is, I mean, expected to be small, because I'm assuming that I do a good job constructing the u0, then I plug it into the equation, and then I get some linear term here. This is nonlinear, and this is a defect coming from how bad or how good my initial approximation u0 U naught was. Okay, so the strategy is to try to sort of invert the linear part onto the rest. Okay, so if assume first that we can invert this operator, and this is a big if, then in principle everything should work because this is like epsilon square, this is small, and therefore I need to prove that this is smaller than epsilon. So if small is sufficiently small, no matter what constant, how big I put a big constant here, then I win. But of course, small needs to be sufficiently small. So there is this game with the numbers, with the C and the small, that they need to be suitable. Okay. So if all that happens, then we can close using a fixed point argument, like a Banach fixed point argument, and then we can prove the existence of a solution U bar in a small ball, and therefore that will imply a solution of a solution U. And if our U naught was sufficiently convex, then since U bar is very small, this is not going to destroy the convexity from U naught. Okay, so this is the plan. The plan is that if U naught is good enough and U bar is sufficiently small, then we win. But let's make all these rigorous, and let's figure out how to prove all the ifs that I claimed. Okay, so now this is sort of a summary of what one has to do. We need to construct a good approximation U naught, prove that this operator is invertible, and then check that the constants are good enough. Okay, so I will only talk about points 1 and 2. Okay, so the first thing that comes to mind is to say, well, let's try to do formal asymptotics of the solution. And then, well, the first drawback is that, okay, the first term is easy. The second term is not so easy, because now this is not a guess. This is what it has to do, like what it has to be by doing formal computation. So this is not, it's a transcendental number. So this is a solution of some equation, and then there are more terms which are sort of like nasty numbers. So even if one does that and figures out the exponents, then the problem is that, okay, very close to 0, you're doing very well. This is very well, but this is pretty bad. Okay, so this is not tolerable given the errors that we need to beat. So we need to find a different way. Okay, let's try to refine, and then let's pay a price to sort of move this thing down at the cost of perhaps moving this thing a little up, so that they can kind of balance. So we're going to add some cosines. Okay, and if we add some cosines in a way to lower this thing down and to make this thing go up, then we have some kind of better global control, and we don't need to add a lot. So just 10, 12 modes should work. But the problem is that even getting something like this, this is way, way far from what we need. And the natural choices to compute this solution, which could be like Fourier series or Chebyshev polynomials, don't work. But instead, we chose to use as our sort of basis what is called the Clausen functions. Okay, so the Clausen functions are given by this series. One can also write this down in terms of polylogarithms. But these functions turn out to be extremely well suited for what we want to do. So they are periodic in X. They have singular behavior at 0 depending on this exponent. Like one can control the singularity based on this exponent. They interact very well with Fourier multipliers as long as they are powers, but they don't need to be integers. So as long as they are powers, these functions interact very well. And there is a huge performance gain in the sense that just putting 10 of these beats by a magnitude of 10 to the 3 or even 10 to the 4 what we were getting with 5,000 Fourier modes. Okay, so now life seems to be sort of good in the sense that we have 20 functions, complicated functions, special functions, but we don't have like a zillion modes. Because even with the 5,000, we were very far from beating the number. Okay, so now our approximate solution is a combination of these Clausen functions to sort of get the asymptotics right, and then some cosines to lower down the tails. Okay, and yeah, there are roughly like 10 here, and there are roughly like 10 here. This is the order of magnitude of the things that we need to put in order to get like a very good approximate solution. And of course, the powers that appear are sort of nasty because they solve this equation, which is not pleasant, but I mean, it is what it is. Okay. So we sort of, remember, this is just to fabricate an approximate solution, and we don't care how we find the coefficients. So we find the coefficients just by minimizing or trying to minimize the defect, and the defect is going to be measured in some weighted L infinity, and we can choose the A's, which depends on the previous A's, just to push down the defect. So this is a nonlinear equation, but since we can solve it any way we want, it doesn't matter. Okay, and this is how the error turns out to be after like 10 plus 10. So now we are beating what we were getting before by a factor of 10 to the 4. And using like a lot less modes. Okay, so if people are interested in the implementation, we also had to suffer a little bit because nobody has computed these things rigorously before. So there is no implementation of the Clausen functions. There is some implementation of the polylog, but it doesn't work. I mean, it works, but it doesn't do what we want it to do, in the sense that it overestimates if we pass like large interval arguments. So for singletons, it does work well, but if we try to compute ZZ of an interval, then the enclosure is massive, and this is not admissible. So we had to implement our own Clausen functions. And we use it. We use the monotonicity of these functions together with the Taylor expansion and the previous implementation of the singletons. So together with that, then we can get like nice enclosures at the price of working with multi-precision. Okay, so double precision is not enough, and because the numbers that we need to treat are very small, so we need to work with multi-precision. But it can be done. I mean, this is not a big deal. So now these functions sort of helped us by crafting a nice approximate solution. Concerning step 2, then the main observation is that, okay, this operator here is compact, which is good because we thought that, okay, maybe we can try to do some sort of bootstrapping. And if we feed it into the operator something, then we get something better out of it and try to do some kind of Neumann series or something like that. But this is not the case. I mean, despite the compactness, what we're working here is about the size, not so much about the regularity. So essentially, if I feed this operator something which is x to the n, then I recover something which is x to the n. So I'm not gaining by applying this operator many times. I cannot, doing a Neumann series is not going to work in that sense. Okay, so this is the guy that I need to invert or that I need to bound. Remember that we are trying to bound 1 minus this. Okay, so I can write this in a compact way as some kernel acting on F, and we work in L infinity based spaces in weighted L infinity. So as an operator from L infinity to L infinity, the norm of this thing is given by the mixed norm L1 L infinity of the integral. Okay, so I need to compute the L infinity in X, L1 in Y of K. Okay, this is the sort of thing that they have to compute, and I need to hope that this is actually smaller than 1 so that I can invert 1 minus K, and it turns out this is barely smaller than 1. Okay, so we are safe, but by very, very, very little. And this is not a bound. This is the actual number. So there is no overestimation here. This is actually attained at x is equal to 0. Okay, so even if we were able to do this, then the price that we pay is that we need to compensate with very small defects, because now the norm of the inverse or the bound on the norm of the inverse is very high, and we need to compensate very small defects. So there is no chance I can do this by hand. I mean, there is no way I can get such a good estimate, which is sort of barely passing. Okay, so this is one argument in favor of using a computer for this. I honestly don't have any clue as to how to do it without the computer. Okay, so now how to prove this red estimate? Well, I'm taking a soup in X, so I'm going to decompose it whenever X is small and X is large. If X is small, then we do asymptotic analysis. So we expand around X is equal to 0, also because the kernel is singular and we need to avoid like 0/0 situations. And this is done by hand. There are many terms. They are harmless, but there are many of them. And then for the rest, we do a computer-assisted calculation. So this also has the advantage that the norm is not attained here. So the norm of this thing is attained whenever X is equal to 0. So if we move a little bit away, then we have a little bit of room, and that's enough. Okay, and as I mentioned, the kernel sort of looks like this, but also this term is sort of big in some regions, so we need to expand a little better to sort of have control on everything. And on top of that, there is this operator is singular. So whenever there is a singularity here at y going to x. There are other singularities as well, but this is probably the most problematic. Okay, so let me briefly explain how to compute like singular integrals. So let's take the paradigmatic example, which is the Hilbert transform. So the Hilbert transform is this integral over here. PV stands for principal value. And then I'm going to split it into the far part and the near part. Near, I mean near to the singularity. So this one is good. And let's see what, because this is not singular anymore because I'm working in this far region. And then to deal with the first one, then one just simply expands, assuming enough regularity in F. So one can expand here, you get like a y times F prime, and this y cancels out with this one, and I can bound this. Okay, so I'm not really using here that this y is y. If this y is like y to the 1/2, then one can do the same trick with the immediate changes. And then we can bound this. This is an error, and then we have the main term here. So this is some of the things that we need to use in order to bound the singular integral operator that appears by means of the k-naught. Okay, and of course we can optimize on where to put the near far boundary. Okay, so now we close. We work in this weighted space. And we can close in a small ball. And okay, there is a technical issue here because this is proving barely the asymptotics, but we can also deal with it by perturbing the weight. To go from here to the convexity, then we just do the same, but with C2 estimates. There are more terms, but the same principle holds. And the numbers keep being sensitive. This 0.996 keeps appearing. Okay, so let me move on to, to the uniqueness. The main question is, okay, is this convex traveling wave that we found the only solution? And as in the Euler case, this is not necessarily implied by the existence proof. There are also solutions which are like 2π, like pi periodic, for example. You may wonder something like this. And of course, this is 2π periodic as well, but this is kind of cheating. I don't want to say that there is non-uniqueness because there is this one versus just this one. Okay, so I want to work in a space where this is not allowed. And to do so, we're going to impose monotonicity of the profile. So if we assume that the profile is monotone and even, then we're going to show uniqueness. Okay. Okay. So this is the theorem. I will explain the picture in a minute. The theorem essentially says that, that there is a unique periodic traveling wave solution of greatest height, which is monotone, and it's 2π periodic. Okay, and just to fix ideas, this picture, this is U. It looks a little weird. U of x over square root of x, and this is x. Okay, so remember, U had to be like this, and U over square root of x sort of looks like this. And this is the true solution, the pink one. And I will explain what the blue and the other colors are. Okay, so the main idea here is the following. Pretend that we had a priori bounds, upper and lower bounds. Then can we refine those bounds to get better bounds? So this is the main principle. Then if we do so, and if we can prove that the successive approximations converge to 0, then there is uniqueness. Because at some point, we can apply some contraction mapping argument to show that between these two bounds, there is only one solution, and therefore between these two bounds, there is only one solution. Okay, so this is the main idea. And keep in mind that we don't have maximum principles here. So essentially, if we go back to this picture, this is like U naught, this is U1, dot, 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 and this is UN. And the same, okay, minus, 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 and U naught plus, and so on. Okay, so this is a numerical plot of our bounds and how we get there by refining the solutions. Okay, so as I said, the numbers here are very delicate. We're going to use the computer to bound them and to get the most of them. And the operator is not monotone, so we cannot use like maximum principle sort of type of techniques or positivity arguments or things like that. And there is no general contractivity. We only get contractivity whenever we are close to the solution. So if we try to prove some contraction mapping argument from these two bounds, then we fail. We need to be extremely close to the actual solution. Okay. So this is sort of how our equation looks like. Now I'm sort of, for convenience, I'm multiplying by this weight because it's better to work with the function w. But essentially we have a quadratic part, w squared, and then two operators, f and g, which are positive. Both f and g are positive, have positive kernels. So if w is positive, then f is positive, and if w is positive, then g is negative. Okay, so these are the ones coming from the K naught that I wrote before. So there is some competition between these two things. There is no positivity from the operator a priori. So these operators f and g are competing to get a sign. And if you look at it, it's very similar. F and g are very similar. The only thing that changes are the integration regions. So from 0 to y star, k is negative, and from y star to pi, k is positive. Okay, so this is what determines the positivity or the negativity of the operators f and g. This is more or less how it looks. This is y star, and this is a linear approximation. Okay, so this is sort of how it looks. And then from here, k is negative, and here k is positive. Okay, so this is just an extra layer of problems. So the proof is going to be the following. So we're going to prove a priori bounds using the equation. Then we're going to iterate those bounds using the monotonicity of the solution. And then finally, we are going to reach a regime where we can do these iterations in a more like large scale way. Okay, so how to get the a priori estimates? The a priori estimates are probably not so important. We use the equation, and then we can get some bounds. And we need to bound y star at the same time. So bounding y star is also part of the problem. It's not difficult. It's more annoying because y star is essentially the zero of k of x plus y plus k of x minus y minus 2k of y. This is for every x, one needs to find the y for which this holds, and one can enclose that solution very well. So we can get an upper bound, which is of the form 0.84 plus something, and the lower bound, which is 0.19. If you look at the original picture, we need to go essentially to 0.62. So we are starting just here and here, like 0.84 and 0.16. Okay, so now we are here. And if you remember, we had w squared is equal to fw minus gw to the 1/2. No, sorry, like this, but w is not. So a very natural, and then since f and g are positive, then a very natural operator for a candidate to improve bounds is to say, well, I put here the mean and here the max, and the other way around, and this will give me a new upper bound and a new lower bound. Okay, so then the natural operator to define the iteration should be these ones. Okay, and of course I don't want to lose just in case, so I compare it with the previous iteration and I get the best out of what I had before and what I have now. Okay, the first main difficulty here is that now with the bounds that we have, with this w naught plus and this w naught minus, then this is not necessarily positive, the thing inside the root. So this is a problem, and we just cannot apply the scheme like that. So we need to work more. Okay. So we can work more using the monotonicity of the solution, now taking into account the structure of the integrals in a clever way, and getting estimates of these guys. And with that, we can improve the bounds a little bit and get to 0.73 and 0.33, which is now good enough to apply these operators here. Okay, so now we are in a position where we can use this operator J. Okay, and just for comparison, Kobayashi, when he proved the uniqueness for the water waves problem in 2010, he got the Moore Prize for that paper. And essentially what he was doing was this, like the whole paper is just this piece of our proof with a simpler kernel in the case of Euler. I mean, both are explicit, but the Euler kernel doesn't involve a series. It's just a function. So this is sort of similar in the spirit of what Kobayashi did. Okay, so now the problem is that the gain now, like the J tilde that I found before, saturates. And now the J improves, but very, very little. So we need to do a ton of estimates, like a ton of iterations like that. So let's try to do it using the computer. And instead, the iterations of J are going to be done via the following problem. So now we're going to approximate our function, not by a polynomial, but as some collection of piecewise step functions. Okay, many. I'm going to put many intervals here. And we're going to look how the operator F and how the operator J act on this basis. So I'm going to, I have two indices. I'm going to see when I put a characteristic function supported on the interval xj minus 1 xj, how does it act? And what does it create in the interval xi? Okay, so because the problem is linear, in what's inside the root is linear. So if we understand this, then we understand the whole problem. Okay, so we need to see in this finite dimensional but big space how do these f and g operators act. So by doing that and by discretizing that, then we get an idea, and then we would essentially apply the operator j in this discrete setting, and of course all errors are taken into account. Yeah, now the drawback is, well, if you look at f is the integral on something, there is the y star on top of that, and the kernel is unpleasant. How are you going to do that? Because you need to do this like n squared times. Times the number of iterations that one wants to run the procedure. And then one way to help out the computer is to do some of the integrals by hand. And by doing so, we get more special functions. I've learned a lot about special functions doing this. So if one looks at the Fresnel integral, which is defined that there are a few equivalent definitions, but let's take this one. Then this integral can be written down as these little f's, which are in turn functions of the Fresnel integral. And these are finite series with a medium-sized amount of terms. And the Clausen functions also come back. So we have these special functions appearing. And by doing so, we can speed up the calculation of the integrals. This is just one example. At least the Fresnel integral is already implemented, so we don't have to do this ourselves. And as a bonus, this is just one example, but there are other instances where we need to also work with a 2f1 hypergeometric function as well to speed up the calculations involving the integral. So that makes the program to be feasible to run in time. Okay, so now we have gone from blue to red. So this is the improvement in this last pass, and we still have to go to pink. But the problem is that the J saturates there, so we need to go back to the original operator. Okay, so in this, from blue to red, there is one operator that works, but from red to pink, there is a different operator that works. So we need to swap again. And now if we do so and suffer again, then we get to the pink. Okay, so now we're almost there. We have some, I mean, we don't see the upper bound and the lower bound, but you can think of this as being like two closely related functions and a small gap in between. Okay, so now in that tiny strip, then the map U to square root of LU maps X onto X. That's good. And if we manage to show that it is contractive, then we are done. So if we manage to show, in other words, that this C is smaller than 1, then we can apply a fixed point argument and show that within this space X, then there is only one solution of the equation. Okay, but of course, life is not easy. So that C is bigger than 1, not by a lot, it's something like 1.1 or 1.2, but still not enough. So given that we have gone all the way up to here, we're not going to give up at this point. And then we put an extra weight. And the extra weight doesn't really change the behavior at 0, which could be problematic, but somehow balances out the tails a little bit, and it somehow serves the purpose of making the C smaller than 1. Okay, so now in this weighted space, we can prove a fixed point argument, and then we can show that the approximations tend to 0. So then there is a unique solution in this space X, which in turn implies that there is a unique solution in the space of even monotone functions. Okay, so just to finish, here in this uniqueness part, we're using a lot of the monotonicity of the solutions, and no monotonicity of the operator. And we can prove, as I said, that there is a unique function that there is even and monotone and convex that satisfies the equation. It's a traveling wave, and this is naturally the solution that we found in the existence part, because there is only one. And the solution satisfies the predicted asymptotics. So let me stop here. Thanks a lot for your attention. I'm happy to take questions.
Thanks a lot, Javier. If there are questions, we have plenty of time for questions.
I guess that Professor Pfefferman has one. Yes, you must unmute. Yes.
So thanks. So suppose we are looking at some other problem. What are the telltale signs that will suggest to us that these techniques might work? Can you give a litmus test that would say maybe?
Well, the point is that this is very general. So as long as you have, it probably has to do with the dispersive multiplier, but it's extremely general. So as long as you can, okay, you can bifurcate and prove some kind of non-trivial things, then well, I mean, the asymptotics may be different from one equation to another, but most of the equations that I know admit such a thing. Like Euler admits such a thing. Other dispersive perturbations admit such a thing. Like the non-local generalizations of KdV, for example, admits such a thing. And then, okay, whether you get a cusp or a corner or things like that, then it depends more on the multiplier. But from the point of view of the techniques, I think it works in many cases. And I want to advocate for like these special functions to construct the approximate solution, because those reduce a lot like the computing power. And if you try to do it using like the usual techniques, then you miserably fail.
Thanks.
I have another question.
Just to follow up for this, so let's say it looks like in some examples you were kind of lucky in the sense that the contraction constant was 0.99736 or something. So say that it was slightly above 1. Would there be a way to just adapt? Or
yes,
in order to make this work?
Yes, it's unpleasant, but then you have to sort of split the domain. You need to work, and assume that that you have a finite amount of bad directions, which is the easier version of the bad case. Then probably if you split it into the bad directions, which you can control, and there are finitely many, and the rest, which you have like a good constant, then you can probably make it work. But then you need to, then the nonlinearity is dangerous, because you need to see how bad interactions and what does it produce in the bad versus good splitting, and good bad and so on. So there is a way, but that requires more work. But I'm not claiming that you cannot do it. It's just unpleasant, because you need to split your sort of phase domain into the good directions and the bad directions. Maybe if you're lucky, but not so lucky, maybe you have a symmetry and you have an extra parameter where you can sort of get rid of as many bad directions as you have. Some equations may allow that. And via some extra parameter, you may be able to get rid of the bad directions just by choosing the parameter to be in the stable manifold or something like that. Another way, if you want to cheat, is to change the weight. Then, okay, you prove something different. But But we saw that by tuning out the weights, we were getting different constants, and some were admissible. But of course, you prove a different thing.
And you were not solving for the weight. You were kind of, it was maybe some sort of ad hoc.
Well, the weight was sort of determined by the conjecture, because Enstrom and Valen argued that the next order term had to be like x to the 1 plus eta. So we had to put the weight x to the 1 plus eta, or at least x to the 1. It would have been a lot easier if we had been allowed to choose a smaller weight.
Okay.
But then since they wrote that, then we had to do it like with that weight. So we were forced by the conjecture to the choice of weight.
Okay. Thank you.
May I ask, so your uniqueness proof, you showed that monotone solutions are automatically in the space X, and in X you showed uniqueness by a fixed point argument.
Yes.
But what about non-monotone solutions? Are they?
No, because non-monotone you have this there is non-uniqueness, because you may have something like this with twice the period.
Okay, so that's so to say a trivial non-uniqueness, which is so to say, well, which is clear. But could there be other solutions which are truly non-monotone in the sense that something happens in the middle of that where the minimum is? There's another bump or whatever.
I don't know.
So so your uniqueness always is only for non-monotone monotone solutions, and you don't know anything about others.
No, it's not something that we have looked at. We wanted to rule out this like twice the period kind of thing, and the natural assumption is to say, well, if we work in a monotone space, then this cannot happen. And this is also the assumption that people put like in the Stokes problem. So in some sense, we were looking at those papers as well. So the assumption that people in the water waves community consider for this kind of uniqueness or non-uniqueness problems is monotonicity.
But physically, it looks very reasonable to assume monotonicity, but mathematically, it's not so clear.
Yeah, well.
Okay.
Just out of curiosity, if you take something with two peaks, is the height from the crest to the trough bigger or smaller than the height for a single peak?
I think it's smaller. I think it's slightly smaller, but I'm saying this sort of off the top of my head. Give me 2 seconds, I'm running out of battery.
You have to lose the speaker.
Yes. Yes, I'm back, sorry.
I have a second question if nobody else is.
Go ahead.
So it's not quite clear to me about this kernel K. You said it behaves like 1 over square root x.
Asymptotically.
Asymptotically, but you're not calculating with this asymptotics for the K, but you're calculating with the true K. Or what?
That's right. But for example, if I need to do a small x expansion, then I take the 1 over square root, and then the rest I put it into an error, because for small k, it behaves like 1 over square root of k plus a smooth piece that I have under control. This is just to get a feeling of how bad the singularity is inside the integral. But of course, when calculating, I use the full k.
Get an additional error term just by this approximation that is incorporated in the usual error, which you anyway have in the approximation process.
Yes.
Okay, then I understand it. Thank you. So maybe another question on this this bound, which is very close to 1. So there is the u0 in the denominator of the left-hand side. Can we just influence the bound by choosing another u0?
You may, but then the defect is going to be extremely bad.
Yeah, so that's well, okay. So if you for the bound of the inverse operator, instead of 380 or what you had only 10. Then possibly a slightly worse effect is okay.
No, I don't think so, because the problem is that the bound is attained at x is equal to 0. Okay, so you need to really put into, and say the tail, what you put in the tail for u0 doesn't matter. Neither for, like, it doesn't matter for the bound. Okay, so the u0 that you have to put has to have the right asymptotics at 0.
At 0.
Yeah, which is the only thing that matters. Then, okay, you can influence the tail of the k, but that, okay, may help you a little bit to get slightly more decay, but getting the actual number, you cannot do better than that. That's
I guess so, but I just wanted to be sure.
Yeah, no, if it had been, this is sort of what it happens in the last step of the uniqueness, that the maximum is not at 0. And then you can tune in with a different weight, which is sort of similar as changing the u0. And that you can lower things sort of far, like at x is equal to 1, say. But at x is equal to 0, you have no choice.
How big is this computer-assisted part in terms of time, of computation time?
For the first part, like the existent part is a few hours, and the uniqueness part is a few days. Yeah, the matrix part is just big, even with the special functions. So for the existence part, we can do it in, I don't know, 4 hours, something like that, even at the C2 level. So I presented only the L infinity, but even if we go to higher regularity, like C2, then this takes, I don't know, 4 hours, something like that, by tuning the parameters and the tolerances and playing around with them. Whereas the other one is much bigger. Like the matrices are quite big, and it takes a few days.
What do you mean by quite big?
Like 1,000, on the order of 1,000.
And you have to do that many times with interval arithmetic?
Yeah. Yeah, the problem is that the gain, yeah, so it's these two matrices, F and G. Then we can define the iteration as W to be the square root of F. This is now a matrix times a vector, and this is now a matrix times another vector. So once you pre-compute the F and the G, this problem is linear in the W's. It doesn't matter how many iterations you have to do. That's not the relevant parameter. Like you can do many iterations, and it's only matrix times vector operations. But the problem is to pre-compute the F and the G. So given the partition, you pre-compute the F and you pre-compute the G. And this is independent of everything. Now, once you have that pre-computed, then it is fast, but the pre-computation takes time.
Any other questions? Well, then let's thank Javier once again for a wonderful talk.
Thank you, guys.